Hello everyone, we are Group 1 from Operating Systems class, University of Technology Malaysia. My name is Ung and my fellow group members are Kenneth and Yeap Eng Jau. In this presentation, we will talk about Deadlock and Resource Allocation Graph, also known as RAG. Now, what is a deadlock? So when there are two programs that want to use one same resource at the same time, and they both do not allow the other to use it first, deadlock occurs. In other words, deadlock happens when all the programs or processes are waiting for the others to release their resources. Okay, more precisely, deadlock happens when these four things happen together. First, mutual exclusion, which is when the processes cannot share the resources with one another. Second, hold and wait, where a process occupies and does not let go of its resource to be used by others. Third, no preemption. This means that a process cannot actively snatch a resource away from another process. Fourth, circular wait. This condition is where all the pending processes are waiting for one another. For example, A waits for B, B waits for C, and C waits for A. Therefore, once again, when all these four situations happen together, deadlock happens. Next, we look at Resource Allocation Graph or RAG. Now let's say there is a process and there is a resource with four instances. A process is like a person, a resource is like a box, and the instances are like the items inside that box. So when the process or the person makes a request to the resource, which is the box, he is actually requesting for only one item in the box. So when his request is approved, then the item now belongs to him. In other words, the process, he is now rightfully holding an instance of the resource box. So the acts of requesting and approving is called edges, and they are represented by arrows. When process makes a request to resource, a request edge is formed. When the resource approves the request, an assign edge is formed. Now, since deadlocks can cause a computer to lag or even to stop working properly, deadlock avoidance algorithms must be executed. The algorithms check if deadlocks will occur. If yes, then the request is delayed. In fact, deadlock avoidance aims to guarantee that a system does not enter a dangerous state. In addition, a different type of RAG with a slightly different set of edges can be used. For example, before the process makes a request to his targeted resource, he must make a claim first to announce what is the maximum resource that he needs. Then, he can only make the request after the claim. After that, as usual, he will be assigned the instances from the resource box, and finally, after he's done using it, he releases the resources and makes a new claim to his next target. On the other hand, deadlock can be detected by converting an RAG into a wait for graph. For example, this is an RAG. Now, by removing the resources, we now only show which process is waiting for whom through the arrows. We can now detect if deadlock will occur. So in this case, we see a circular wait in P1, P2, P3, and P4. So a deadlock may be occurring. Okay, as you may have already realized, a deadlock situation in an operating system can be better explained by using a real-life example. So now I would like to invite my fellow teammates to show you how deadlock occurs in real life. Thank you and stay tuned.
Thank you Ung for his presentation. In this project, we will discuss deadlock by using Resource Allocation Graph, RAG, using real-world application. With the help of RAG, we can clearly observe the current relationship between each process and the corresponding resources. In our case, we intend to describe deadlock by using an example of a cashier counter in a supermarket, where each counter requires a cashier or a supervisor in order to operate normally. We will be discussing what happens when a cashier in a counter requires assistance from a supervisor. So in our real-world application, the cashier or the supervisor will be acting as a resource, while the counter will be acting as a process. During peak events like Members' Day, supervisors will look for temporary employees to guide them to help out as a cashier in a counter as well. So this is the example that we're going to propose, where the cashier, the temporary employee, the supervisor will be acting as a resource, while the counter will be acting as a process. Here we'll be demonstrating the flow of RAG with various edges. So the first edge will be the claim edge. In this situation, the cashier might need help from the supervisor. So in this case, the cashier is just claiming for the help from the supervisor. After the claim edge, the claim edge will be changing into a request edge when the cashier 1 requires an urgent help from the supervisor in counter 2. After the request edge will be changing into an assign edge when the supervisor is assigned to counter 1. After we have known the various edges, I'll be describing a case without deadlock. So in this situation, the cashier counter is working normally. In this case, both counter consists of a cashier or a supervisor. Since both counters are not claiming or requesting help from each other, therefore, both of these counter can operate normally without having waiting each other. Over here, I've converted the situation into a resource allocation graph. A cycle in a graph implies that the system is in an unsafe state where deadlock might occur. But in this case, you can see that cashier is being assigned to counter 1 and the counter 2 is holding supervisor. As you can see over here, there is no cycle occurs. Therefore, the system is in a safe state and deadlock doesn't occur.
Hi, I'm Yeap Eng Jau. Right now, I will be presenting for the case with deadlock. So before start, let me explain about the situation right now, which is the cashier requests help from supervisor. So as you can see from the right hand side, the cashier are requesting help with the supervisor, which is he say, I need your help to void my bill due to double scan of the products. While supervisor is say okay, but I need your help to take over my counter. Okay, then the cashier will reply, oh, but my counter now is full of customers. I can't leave my counter. At the same time, supervisor also facing the same problem, which is his counter is full of customers too. So the supervisor requests the cashier to wait. So in this case, cashier 1 requests supervisor to cancel bill. So supervisor requests cashier 1 to take over his counter. But both counters are still busy serving customers. So both counters need to wait, hence deadlock occur. So right now, I will be presenting for the RAG with several instances of resource. So let me explain our scenario, which is during the peak event, supervisor will look for an temporary employees and also guide them to help out. Those temporary employees sometimes might need request an experienced cashier to help out. So in the right hand side, it's indicated that the temporary employee and the supervisor, which is our example for the resource with 2 instances, which means temporary employee and supervisor are the 2 instances inside a resource. So we have the 3 resource and the 3 process, which is resource 1 cashier, resource 2 temporary employee with supervisor, and resource 3 is a cashier 3. So 3 of the cashier will indicate about the process, which is counter 1 is process 1, counter 2 is process 2, and counter 3 is the process 3. Okay, so we initially cashier 1 was assigned to counter 2, and temporary employee are assigned to counter 1, and supervisor are assigned to counter 2, and cashier 3 are assigned to counter 3. Okay, so in this problem, temporary faced some problem and he requests help from cashier 1. So he say, cashier 1, I need your help as I encounter some problem. Well, cashier 1 is okay, then he say, okay, please wait a while, and he requests cashier 3 to help out and say, cashier 3, can you help me to take over my counter as I need to go back to counter 1? And then cashier 3 say, okay, but I need supervisor help to wait a bill. At the same time, supervisor he can't leave counter 2 because he's still helping counter 2 to solve some problem. This slide will indicate about our initial allocation, which is resource 1 allocate to counter 2 and temporary employee assigned to counter 1, supervisor assigned to counter 2, and resource 3 assigned to counter 3. From this slide, we can clearly see that counter 1 requests resource 1, and counter 2 requests cashier 3, and counter 3 requests for the supervisor. And from this graph, we can see that it's showing 2 loops, and it indicates that deadlock occurs. Yeah, I think that's all from my side. Thank you so much.
Alright, in a nutshell, deadlock occurs when multiple processes request for the same resources together. Besides, deadlock is triggered when mutual exclusion, hold and wait, circular wait, and no preemption occur simultaneously. However, deadlock detection and avoidance algorithms, such as the RAG scheme, can be implemented to overcome this problem. Furthermore, deadlock can be explained using a real-world application, such as the member day situation mentioned just now. Alright, that's all for our presentation today. I hope it has been informative to you all. Thanks for watching and have a nice day.